Okay. Yeah.
Well, good morning, everyone. Really good crowd on my side. I kind of tried to walk around a little bit and say hello to a few people. If you don't know me or we've not had a chance to talk, my name is Dr. Jeremy Denton. I currently serve as the department chair for math here in the College of Natural and Health Sciences. And I wanted to open this up with a word of prayer and then introduce our speaker today. And then we'll get started. Dear God, I love you, Lord. I'm so thankful for this day and thankful for this university that we can come and one, learn more about you, but also learn more about you and through the lens of academics. God, and I just thank you for this opportunity that we have here just to kind of chat today about what Professor Tessler has prepared for us, God. And we just ask that you would just be with us through this hour, that we would be able to learn something new and just kind of see you glorified through it. In Jesus' name we pray. Amen. Well, our speaker today is Professor Cody Tessler. He has been at SU for 11 years, and he is one of those that is able to teach quite a wide spectrum. He's probably taught more math classes than any of us. He's been all the way through developmental math when we had that, all the way through calculus, and now branched into the SU Tech world. And probably taught 10, 12 courses in between. So he has a wealth of experience here. An alumni of SU, I hope I don't steal too much of his intro. And he is a great, great friend of mine. And we've been friends since I've been here for 10 years. So without further ado, I'd like to introduce Professor Cody Tessler.
Thanks, Jeremy. Thank you. Well, good morning, everyone. Thanks for coming out on this, what feels like a Monday morning, but it's actually a Tuesday. Don't worry, the weekend's almost here. So my talk today is going to be on artificial intelligence from foundations to the future. So it's really not going to be a talk about what is ChatGPT, although we will talk about that a little bit, but really just how did we get to where we are today. So I was really trying to figure out like what topics to focus on. So I was talking to Professor Ullman about this, and of course his idea was, why don't you just put it into ChatGPT and have it give it a talk? So I was like, no, we're just not going to do like all text. So I loaded up another model called Sora, which generates video, and I listed some topics for it to talk about in a video. So I'm like, I'm trying to get out of this. I put it off for 2 years, but let's see if I can have AI do it for me. So I put in the topics, where I talk about tic-tac-toe, decision trees, GPT. Anyway, this is what it gave me. So here's the talk. Just kidding. I think I'll take care of it. I mean, you see tic-tac-toe, decision tree, but the fact that there's a world blowing up here is a little terrifying. So I think I'll take care of the presentation for now. And you can see things like some made-up words, supervised. Over here we have something that looks similar. They're trying to use unsupervised AI. So these are some terminology and a fairly strange picture that comes out of a nightmare. So I'll take care of the talk. But where are we today? Well, on November 30th, 2022 is really the day where I think AI became part of the common vernacular of society. Before that, it was really like, okay, AI is cool, sounds smart, can it do my homework? But on November 30th, 2022, OpenAI announced their ChatGPT 3 public beta. So how many have heard of ChatGPT? Definitely. 3 years later, we definitely had that has gotten around. And in March 2023, they released it to the public, and it was, ChatGPT was, for many years, the most downloaded free app on iOS. That was recently trumped by another app that we'll talk about in a few minutes. But it has continued to evolve quite quickly over the last 3 years. So in November 2022, they had their public beta for GPT 3.5, then they had a faster model 3.5. For about 2 years now, we've had ChatGPT 4 and 4.0, 4.0 mini. Isn't this a great naming scheme? They couldn't just do like 3, 4, 5, 6. No, we have to go ahead and do O's, and then sometimes we don't even like where the O is at, so we move it to the front instead. And this right here is just the evolution of OpenAI's ChatGPT model. So just this last month, O3 Mini came out, and O3 Mini High, which are the next step of their reasoning models. And really, last night, another company announced their reasoning model. I don't know if anyone woke up and checks the AI news, but Elon Musk announced his new GPT model just last night and did a kind of a streamed keynote. But anyway, this is just ChatGPT and its progression of models that have gotten progressively better over the last 2 years. And there's several players in the game. So we have ChatGPT right here with OpenAI. We have this little orange guy. This is Anthropic's Claude, is another major company. We have this one, XAI. You can kind of see the 3 letters right there. That is, the company is XAI. It's one of Elon Musk's company. And they just released their new Grok 3 last night. We have Google still hanging out here with Gemini. Then, probably the one that I think is just the funniest to look at is Llama. This is Meta's AI. And then we also have this big blue whale. Does anyone know what this one is? It took quite a splash about a few weeks ago. Thank you, splash. Anyone know this one? DeepSeek R1. So this DeepSeek R1 was one of the first models that were, these major models that were open source, meaning that the users could go in and see the source code and how it was developed and how it is trained and so forth. And interestingly, it made quite a splash because its claim is that it did something with 2,000 GPUs, or graphical processing units, that Meta was saying they were going to need 100,000 for. So what happened, this big drastic difference in technology needing to prepare and train these models caused the biggest single day market cap loss. I don't know if anyone watches the stock market. A few weeks ago on January 27, 2025, NVIDIA lost $465 billion in the stock market because NVIDIA is like, you need our chips to get these models trained and ready. And then DeepSeek, this big blue whale, was like, we did it with small amounts. And again, there's a lot that goes into that. Again, there's like all sort of like market analysis and like there's hype and all that. But that is just really where we're at with ChatGPT and the various other models. And those were just the big players. There's a bunch of different models that specialize in different things. So we have generative AI. That's really more what you think or hear and see of AI nowadays, is what we, in the computer science circles, is generative AI. Most specifically, you're probably used to working with something known as a large language model, or an LLM for short, but there are other models. So like the model I used to generate that video to try to get out of the talk was Sora. That's a video model. But let's go ahead and see how you are all at recognizing generative AI versus something that's real. So just to kind of wake you all up on this pseudo Monday morning, we have 2 pictures right here. One of them is generated by AI, the other one is taken by a photographer. Go ahead and take about 5 seconds, look at those, and ask your neighbor, see if you all could agree on which one of these is generated by AI. All right, if you think this one on the right is generated by AI, point to the right wall. If you think the one with the blur over there is generated by AI, point to your left wall. All right, let's see how you all did. Yes. So it's getting pretty good. So, and I think you all, I think many of you pointed to that one, so that's very good. And you could kind of maybe see some weird things going on with the fingers. Kind of this, like you can even kind of see it kind of blurs out the spelling a little bit. And you saw even with the Sora model, it didn't do very good with words. So there is 2 scenarios where we have generative AI. Generated a video, it generated a picture. And if you really think about video as just a sequence of pictures really fast, It's really not hard to extend that idea in terms of conceptually, but it is quite challenging in terms of computationally, because for a movie, it's 24 frames per second is the standard for movies. So for 1 second, you have to have 24 pictures. So you can see computationally it'll really speed up. And that 5-second video I showed at the beginning took Sora probably about a minute to generate. So that was just 5 seconds. So anyway, we have generative AI for videos, we have it for pictures, and probably where most of you use it is for text. So go ahead, same thing, ideas before, take about 5-10 seconds, read through those, and discuss with your neighbor which one is generated by AI, which one was written by a child, or a high schooler. I don't know anymore. Gotta be good. Or by me. All right, ask your neighbor what one they think. All right, if you think essay number 1 is generated by AI, point to the ceiling. If you think essay number 2 is generated by AI, point to the ground. Oh, we're much more mixed. Take a look. All right, let's see how you did. The one generated by AI is wrong. So even, by the way, have you noticed that some of the professors didn't get that? This is not a talk about whether you should use it for your homework or not, just saying. But if you kind of look at it, these models have certain things that they use. Like if you look at the language of the first one, look at how much more flavorful it is, how much more yummy it is. Sorry. A yummy sandwich, a cold juice box, a tasty piece of fruit, a crunchy chips. There's a lot of flavor to that. Where if you think about a kid's writing, they don't necessarily have quite the vocabulary to just, so you could see my mother packs me a sandwich, a drink, fruit, and treat. It's not as flavorful. So there's also other keywords. It's gotten better. Like there was a joke that Professor Allman and I had. If you looked at the first models of ChatGPT, it would pretty much use the word delve every other sentence. It's like let's delve into this topic and so forth. But and again, this is generative AI, and we're going to continue to see these evolve, and they will be wonderful tools. And there's still a place for having a good foundation in whatever subject you're working with. So again, it feels almost like magic, some of these tools, and hopefully, and one of my goals today is really to dispel some of that magic. So you kind of see historically, where did we come from to where we go, and how did we get to these really tools that look like magic today. So zooming out a little bit, generative AI is just a small piece of, and again, this bubble should really even be bigger, artificial intelligence in general. So we're going to go ahead and kind of look at a little bit outside of what's this generative AI bubble and look at some of these ellipses. Like what are some of the other things, especially those that really set the foundation for these tools and how they work. So we'll return to generative AI and GPTs at the end of this, but let's go ahead and lay some foundational work. Well, let's think about things that we've probably actually been using AI before these current ChatGPT, Claude models. For example, how many of you have gotten a spam email lately? How many have even looked at that spam email? No, because we actually have some AI that's looking at the messages that come in and deciding if it is something that needs to go in your inbox, if it were spam. And if you think about how much email comes through nowadays, it's not like someone at Google is sitting looking at all your messages, hopefully not, and being like, oh, that one goes to the inbox or that one's spam. There's not a human sitting back there, so they trained some intelligence to think. I think they really just have an algorithm that is looking at features or characteristics of email and have decided whether something is should go to your inbox or spam. So we've had spam filter around for several years, and this was an artificial intelligence algorithm. Another one that we'll see commonly is text handwriting. So I don't know about you all, but my handwriting is definitely not that good. But as humans, no, that was the edge of the page too. There we go.
That was great.
So look at that. You all could recognize my handwriting despite it not being as neat as that one up there. So we have handwriting recognition. And we'll look at an example of how a deep neural network is used to identify handwriting later in this talk. So pray for me. We also, how many have watched Netflix or some sort of Disney Plus Hulu over the weekend? You see the first thing that it gives you is some recommendations you to watch. And how many of you just breeze by those recommendations and continue to look for the catalog for 45 minutes simply to watch nothing? Is that just me? Okay, so again, well, those recommendations are looking at your watch history to make those recommendations. And even really more than your watch history, they're probably also looking at your demographic. For example, Netflix has never recommended The Bachelorette to me. So it's not just, it's probably looking at, oh, okay, it's male, mid-30s, probably not interested in The Bachelorette.
Are you watching it on someone else's account?
Someone else. So we've been working with AI for quite, in a lot of different scenarios already, not just ChatGPT. It's really been a part of our lives for several years. So where AI probably shows up kind of most naturally and where it is developed from is in games. So someone under the age of 30, please. What game is this? Anyone under the age of 30? Oh, okay. Yeah, so it's a two-player game where it's like table tennis. Matt, what system did this come out on?
Atari.
Atari, yeah.
Okay.
Excuse me.
Oh, you mean yeah. Hard.
So right here we have some idea of the game, and maybe you don't have any friends, so you're like gotta play by yourself, or maybe your all friends go to bed at 9:30, Professor Almond, and they can't play. So this is an example of a game where it'd be nice to have an AI for, but really let's simplify it and set a goal. So there's another game right here that we're gonna look at, just so we don't have two paddles, but we have one paddle right here. Does anyone know what game this is? I think I have a little clip here.
Asteroid?
No, but I played it, but I can't remember.
It does start with a B. It's a breakout. So the principle of this, the idea of this game is that the ball will basically bounce back off of the bricks at the top, and you got to break all of the bricks. So we're not doing very good here. We're going to look later at we're going to look at reinforcement learning, and that's how this AI learned how to play this game. So it wasn't very good. It only got a score of 3 points. It lost some lives, but what are we trying to do? Artificial intelligence. So it might be nice to think like, how would you play this game? Well, how would you? Well, if you have, let's say, this scenario right here, and let's say that the ball is coming down right here. What are you going to move, or how are you going to move the paddle, left or right?
Left.
You're going to go ahead and move the paddle to the left. What about this other scenario right here? Let's say that the ball is going over this way. What way are you going to move the paddle? Right. So you have made some decisions. So what we do historically with a very basic artificial intelligence is we make something known as a decision tree. We saw some input and we decided to go left or right based off of that input. So if you think about a tree, there is the roots, and in computer science they invert this tree. So this is the root of the tree. So is the ball left of the paddle? You ask that question and you answer it either yes or no. So in this case, is the ball left? So the ball left of the paddle. Yes or no right there?
Yes.
Yeah, so you would answer yes, so let's go ahead and move the paddle to the left. But what if the answer was no? What if we had the other scenario? What are you going to do?
Move paddle to the right.
Move the paddle to the right? How many say move the paddle to the right?
Or not move it.
You're like, feels like a trick question. And it is, because if you really don't want to immediately move to the right, you want to ask a new question. Is the ball right of the paddle? And if it is, yes, that is when you move the paddle to the right. What is the other scenario that we haven't really talked about yet?
If it's right underneath it,
If it's right underneath, what are you going to do?
leave it there. Leave it
Don't
there.
move. If the answer is no, don't move the paddle. So this decision tree, here's basically the algorithm that we have a decision tree to go ahead and play the game of breakout. So if in Introduction to Computer Science, we learn how to program, and what we have up here on the screen right now is pseudocode. So we have this idea of while the game is ongoing, so you haven't lost yet. So just continually make these decisions. If the ball is left of the paddle, move it left. If the ball is right of the paddle, move the paddle to the right. And the last scenario, no condition, it's just the third scenario, don't move the paddle, you're ready to go. So this right here is a decision tree. Fairly simplistic tree, but you probably use decision trees in a lot of your decisions every day. So for example, how many of you had a cup of coffee this morning? A couple of you. How many think they want a cup of coffee right after this talk? I'm not going to read into your answers there. But there's things that go into that decision right here, like how much is it? How cold is it? How much does the coffee cost? How cold is the coffee? And you might prioritize these different decisions more, and you'll have kind of mentally this decision tree that you've built out to make these decisions. But as I mentioned, games are really where we want to focus. So anyone, what game do you think we're in the midst of playing right here? Tic-tac-toe. So let's see, okay, so let's say right now is XO, XO, so let's say X went first, is X's turn right here. So let's see, who wants to finish, who feels confident in their ability to play tic-tac-toe? Dr. Shaw, you help me out? All right, so your X, make your move. All right, so you're going there, okay, so let's see, Dr. Shaw played there, where should I play? Bottom right, okay, I like that. I'm gonna crowdsource and make sure you don't beat me too bad. All right. So where would you go next? So you're gonna go right there. Oh man,
2 moves.
2 moves. You crushed me. So X run right here. So how many have played tic-tac-toe? All right. How many besides me has lost at tic-tac-toe? Okay. Do you have to lose at tic-tac-toe? No. Oh, I didn't get this. So, there seems to be a strategy where you don't lose. So what is that strategy? Well, we might try to, thank you, Dr. Shaw. We might look at a decision tree like this that I really didn't have the time to think through, and y'all didn't help me with that. I'm just kidding. But can I get 3 in a row this turn? So if you can get 3 in a row, what should you do? Do it. Go ahead and win the game. Play the square. And, well, what if no? What would maybe be the next thing? If you can't get 3 in a row, what is maybe the next question you want to ask while playing tic-tac-toe?
Can you block the other?
Can you block the other person? So can my opponent get 3 in their next row? Well, in that case, well, if they can, let's go ahead and block it. And what about the scenario of no? Well, that's where it gets a little bit tricky, because we had this trichotomy with left, right, or don't move with breakout. But what about in tic-tac-toe? If you think about the initial board, where should you start? Maybe X decides to go in this upper right-hand corner and says, okay, let's go ahead and just start the game there and see what happens. Is that an optimal move? So there is this sense of like, it's hard to consider every single case, so we need something a little bit more sophisticated than a decision tree. So just to kind of set the stage for where we're going in artificial intelligence, why is AI good at games? inputs and outputs can be represented with that M word right there, mathematically. We'll keep the math simple today, don't worry. With the goal in the form of a function to either maximize or minimize. So we assign values to different gain states, and then depending on whether you're X or O, you're going to try to either maximize that value or minimize it. So let's go ahead and look at an example. And the algorithm we're looking at is known as mini-max. And every time I say that, I want to say Mickey Mouse, but maybe that's just Florida rubbing off on me, but we have an algorithm known as mini-max. Mini-max, this algorithm actually was developed and published by John von Neumann in 1928. It is the algorithm that kicked off a whole branch of kind of mathematics and computer science known as game theory, which is basically where, I don't know how many have heard of the prisoner's dilemma. So it's an interesting question that basically says, if someone, like 3 people are in prison, if they all agree not to rat each other out, they all get to leave. But like if someone rats out someone else, they go ahead and get like extra points as they get out, but then they've really kind of screwed over the other 2 dilemmas. So it's this idea of like game theory, like how should you handle certain social situations. So mini-max is the algorithm that really kicked off the game theory and the branch of math and computer science, and really, so it's really even a part of social sciences. So there's a lot of, it's very far-reaching. But anyway, let's go back to tic-tac-toe. These are the really kind of the 3 scenarios that we could have ended with right here. We have zeros, we have O winning down the left-hand side. Is this the only way for O to win? No, we might have won across the top or the middle or diagonal. We have this draw state in the middle, and then we have X winning on the diagonal over there on the right. So what we'll do with the mini-max algorithm is we'll assign values to each of these different scenarios. So like, let's go ahead and say O has it, that game board has a value of -1. Let's say a draw has a value of 0, and X winning has a value of 1. Again, numbers are small, that's the largest numbers we'll need here. I told you I'd keep the math pretty simple for now. So if this is how we assign values, and we just did this arbitrarily, you could have had O's be 1 and X's be -1. You could have done 2 and -2. Doesn't matter really for this simple of a game. But that means the goal was no longer just to make a decision, but to actually maximize or minimize the value. So the goal of X is to maximize the score. Because if you somehow get to a game with a board or a game state where the board has a value of 1, X is 1. Where O's goal is to minimize the score. That is, if you can find it, if you can basically build a tree to find a game state with -1, O will have 1. So just to make sure we're tracking right here, take a look at this game board. What is the value of this game board? Ask your neighbor, what is the value of that game board or that game state? All right, did your neighbor say 0? Good, because that would have been wrong. So, how many said that this game board has a value of 1? Just by looking down the middle, we see X is 1. Any questions on how we're assigning the values? Okay, so how do we use this? Let's use that tree idea. So let's look at this game board right here. Let's see, XO, 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 1, 2, 3. So it's O's turn right now. Everyone, we see X is up there twice, O's up there 3 times, so it's O's turn. O has 2 choices. Which one should it play? The upper left or the middle? Bottom middle. And you can kind of mentally think about it. If you play that O in the bottom middle, then X plays up in the top left, and that leads us to a certain scenario. Let's actually go ahead and kind of in our head, and this is what like chess and all those any sort of like board game AIs are doing. Again, they're doing it more sophisticated than we're doing because we'll talk about that in a sec. But they're essentially like, you know, like Sherlock Holmes. Have anyone seen Sherlock Holmes with Robert Downey Jr., where he like kind of goes in his head and thinks about how like the battle will play out? Anyone see that movie? Yeah, so that's kind of what Minimax is doing, that in this head, we need to figure out the value of this game state. Well, there's 2 scenarios. Here's that same tree. If O is in the upper left, Well, let's go ahead and consider down that scenario. The value of this board we don't know yet because it's not a draw, it's not a win or a loss, but we do know that that would have got us to this game state. That X would have played, so X would have won right here, so we can assign a value to this bottom left board, and then that would mean that the value of 1 essentially goes back up the tree into this one, and then we don't immediately shoot it up to this one above because there's now a decision. We have to decide, okay, is that the way I want to go? Because O's goal was to what? To minimize or maximize the value? Minimize. So let's consider this other. Go ahead and kind of think through this a sec. What would be the value of this board? Okay, well, you have to go ahead and kind of play out that last move. You played out that last move. What's the value of that board? 0. So there's no decision to make to get that board, so that value is propagated up the tree. And then, what do we say? O's goal is to minimize. So which decision does O want to make? The left or the right branch? He wants to take that right branch. So we would say that this game state has a value of 0. And you can just imagine that was just with 2 moves remaining. If we had 3 moves remaining, we would all of a sudden have this tree. So you would have a value of 1. So that means so if you ever saw that game board, you can immediately say X is 1. You don't have to play it out, but by looking at that value, if that is the actual game state, X is 1. That's how you see in chess, like you're like, oh, it's over. Like they kind of have these endings, like these finishing. Closing is like, oh, that the value of this board is going to lead to a certain outcome. So they're trying to force down into this tree a certain game state that either maximizes or minimizing, depending X or O, white or black. And I will say that well, before I do that, we can actually take this algorithm and we can do that same pseudocode. We can do if player is X, for each possible move, calculate the score for the board. And it doesn't look like there's a lot to do, but the danger here is in that word calculate. Because if you think to calculate a board, you have to go down that tree to find a state that actually satisfies your goal function, whether to maximize or minimize. So again, whether you're X or O, this is kind of that same idea as above, is just you're trying to maximize or minimize. So tic-tac-toe, many of you said that it's impossible to, what do you all say? That you can't lose at tic-tac-toe. The worst case, you draw. And that's because tic-tac-toe is referred to be a solved game. Because really, as much tic-tac-toe as you played, you probably have not seen every single game state right there. There's a total of 255,168 games that could be played for tic-tac-toe. So, but for a human, sounds like for a computer, not a big number at all. The processors nowadays, very fast. But chess is not solved. So for example, chess, in the first 4 moves, how many different possible ways can the first 4 moves play out? Anyone want to take a rough guess? Any chess players in here? Let's see, more or less than 1 million? More or less than 1 billion? 85 billion in the first 4 moves. And there's clever techniques they use, such as mini-maps. They also maybe assign certain probabilities to certain games. Like there's, like in chess, you're like, let's control the middle of the board, so they might assign more probabilities. They may not, the AI may not even compute the first moves. It might just have like some pre-programmed best openings. And this is chess. Did anyone watch there was a documentary that came out, I think like 2016, out by Google, on an AI they created in a game that they played. Has anyone heard of the game Go? This is I think it's Japanese right here, but in the first 4 moves, forget billions, there's 266 quintillion game states in the first 4 moves. And this was actually a really challenging problem. There was a documentary, it's free on YouTube if you're looking for something to watch. If Netflix recommendation system's not working, we'll go with the Tessler recommendation system right now. AlphaGo is a documentary that talks about the development of Google's AI called AlphaGo, which sole purpose was to learn to play the game of Go. And the challenge was to beat basically the best Go players in the world. Did they do it? Well, you can watch the documentary and find out. So, that is again some historical context. To get us more into modern context, what we have really decided is to not try to do all these calculations ourselves and set up algorithms to do that, but we've wanted machines to go ahead and just learn based off of the data that we give it. And the data that we give these ChatGPT and these models are pretty much the internet. So it is a huge data set. So how do we scale these ideas of like trees and mini-maps and computations to something that is large as the internet, which is, you need to go down a lot of rabbit holes there. So one idea with machine learning is something known as reinforcement learning. So I'm going to need a volunteer really quick. Come on down. So, I didn't bring this out until I asked for a volunteer. Go ahead and hold this for a sec. So for an example of reinforcement learning, we're going to look at, she's going to be the robot, and I'm going to basically be the programmer, and my goal is for her to learn how to flip a pancake. So here is my cardboard, a little dry, it's the cardboard, but go ahead and can you flip that? I'm going to tell you whether you did a good job. Good. Let's do it 4 more times. Good, good, good. Not so good. It didn't quite flip. Thank you very much. Let's give her a round of applause. So 4 out of 5, but you notice also that after she got scared that first time, then she's like, oh, I was told good. So she's like, I got this, I got this, I got this. And she got a little overconfident. We're all guilty of that. But this is exactly what some researchers did at the Indian Institute of Technology with a robot. So they did they worked on this reinforcement algorithm. It's called robot motor skills, coordination with EM-based reinforcement learning. So let's go ahead and watch this video and see basically a robot who learned using reinforcement learning. We have sound, but I can So the developers start out by basically helping the robot do a few flips. And you could tell he's practiced that before, like he makes breakfast every day. So the robot is kind of tracking that, and let's see its first attempt. Nice. First try. Don't give up. 3 trials. Well, it got it up. All right. 5 trials. Still 10 trials. Okay. Poor guy. You feel bad for him. It's not falling, but you just want to see him succeed. So 11 trials. Ooh, that one almost got back. So 15 trials. It's flipping. 20 trials. Missed the pan, but he flipped it. So this is what's happening in the background right here. When it's flipping it, and this is after it's been successfully trained, you can see the XYZ axis that the robot hand's moving, and it was trained to basically go ahead and flip. So finally we saw, and you would, hold on, let's see before I how many, oh, I didn't get up in time. I say, how many trials do you think it took for him to learn, or this robot to learn how to flip it? 50 trials. It learned how. So yeah, let's go, robot.
Go, robot.
Remember, if they take over the world, they will want these good memories. So, is that the best way to flip a pancake? So, let's go back to our game setting and we'll return to this with that question I said, is that the best way to flip a pancake? You could ask Gordon Ramsay or any of the chefs, your mom, who probably makes the best pancakes ever. Pancakes sound good, maybe they'll have a chocolate snack. Anyways, let's say we have this scenario right here with reinforcement learning. This is a maze, albeit a very boring one. You could go ahead, the goal, you are the yellow dot, get to the green square, you have won. But this seems too safe, let's put some lava pits on it. The floor is lava. So, let's go ahead and say that this yellow dot has never done a maze before. It just knows that it needs to get to the goal, so it's going to start. You could also, it's going to start to try to get there. So its first move is to go right. And well, needless to say, it does not survive. It is lava. So that's fine. Let's say it is resurrected, goes back to the beginning, but it now knows don't go right. Like there's this like red is learned don't go right. This red was it scored -1. Don't go that way. I don't want to maximize. I want to maximize by getting to the green. Going into the red is a score of -1. So we assign that. It assigns this -1. So it goes up, it goes right, goes down. Well, like I said, never did a maze ago. So okay, it passed away, started over, but at least it knows not to do that again. So let's say it keeps going. Now found another red lava pit. Nope, don't go that way. Try again. Try again. It's not good at recognizing the lava. It hasn't figured out red is bad yet, but it finally made it. Ooh, yellow dot. Okay, we're all more excited about the robot. But anyway, essentially what we have is this path that is figured out. I should go this way to get to the winning game state. Is that the best way to go ahead and do that? No. It has found a way to go ahead and do that. And that's it, that's good, but what has happened, it hasn't really explored it. At this point, it knows how to win, but you'll see a lot of these algorithms, and if you ever notice, like sometimes like ChatGPT might say something a little bit incorrect, it's called a hallucination. And that's because there's a little bit of randomness sprinkled in, so it has a chance to learn more optimal patterns. So that is the idea. So it does this path, yay, good job. That is the idea of explore versus exploit. This is an algorithm. There's a book called Algorithms to Live By, and it takes a lot of computer science algorithms and applies them to human psychology. So for example, how many of you, I don't know, what's someone's favorite restaurant? Let me ask you, favorite restaurant? Well, yeah.
Zaxby's.
Zaxby's. What do you get at Zaxby's?
A wings and things.
What?
A wings and things.
A wings and things. Every time?
Oh yeah.
Is that your favorite thing?
Yeah.
Are you sure?
Guaranteed.
Have you tried everything on the menu?
A lot of it, not all of it.
There it is.
You've exploited the fact that you liked it, but you haven't explored this. So there is this idea, thank you. There's this idea of like there's some randomness programmed into these learning algorithms that they're just gonna sometimes not perform optimally to maybe find something that's a little bit better. And that is where we get the idea of explore. So that is reinforcement learning. So you can see like it might find a more optimal path. So at this point it went up, but instead of exploiting what it already knew, did some randomness to go up to see if maybe there's a more optimal path there. So that's an idea in reinforcement learning that is used to why you'll sometimes see them make a mistake. And I mean, if we dig into this a little bit more, like you could say this game state has a score of -1, this score has +100, and maybe things that are like closer to the winning game state will have a larger value. So the goal is to maximize it, so you try to find a path that gives you a more maximum value. And this is referred to like heuristic. This is where you get like algorithms like A* and so forth. But we talked about that in data structures, the second course in the computer science. Okay, so let's go ahead and return to our breakouts and see in breakout how this explore versus exploit showed up. So 100 training episodes, this is what we saw. And it's kind of like, okay, I just need to win. So you can see after 100 trials, it's still not doing too good. But let's go ahead and see what happens after 200 trials. Is it going to fail less? Is it going to lose lives less? Seems to be getting a little better. It's moving a little bit more. It's kind of trying to predict. Still not that great. So 400 training episodes later, you can see this thing is good. Like it's not losing. It's going to eventually win at this scenario. But somewhere between 400 and I can't remember the exact number. Somewhere between 400 and 600, it explored a little bit, and it figured out, the agent, the player, in this case the you're creating, as it's figured out, the best way to play this game is to get the ball up there. And then it just sits and waits. So if it did not explore a little bit, it would not have found that strategy. So I'd encourage you, next time you go to Zaxby's, try everything.
Will do.
And maybe you'll find something a little bit better. So this is again something you can apply everyday life, like, okay, maybe things aren't working, or maybe you could do better. So you might have to consider life as just a series of experiments, and you're going to explore those. So if you mess up, that's fine. You mess up sometimes, but you have some more knowledge. So that is referred to as reinforcement learning. It's also a type of unsupervised learning. That is to say, we basically assign some values. We said, okay, this winning is 100 points. So there's still some and we had to also stand there and say good, bad. So you still needed some supervision. So there's another type of algorithm. How much time do I have? Till 55?
15.
50? All right.
15.
Still.
Wait, till 55?
How 50?
How much time do you have till win? It's 9:45.
Say again.
It's 9:45.
You got this. All right. So here's some ideas. It would be, we'll quote, kind of get the ideas to where ChatGPT is. So unsupervised learning. We don't necessarily want to have to stand there and watch them say good, bad, so forth. So in unsupervised learning, this leads to something known as deep learning. We get a neural network. How many biology majors in here? How many really love neurology, nerves? So okay, Dr. Franklin's on here, right? So we have the neuroscientists to give us really the idea to where we are using ChatGPT and the things nowadays. This right here, anyone know what that is?
Neurons.
It's a neuron. Neural network kind of gave it away. So how do they work? They're connected and they figure things out. Electrical goes through, but computer scientists don't like the pictures. Here's my neuron. Simple. We have a start node, we have an end node. We have an input and we have an output. So what happens is we have two inputs and they're going to go ahead and lead us to some output. See that same tree structure we saw with decision trees? But what we're going to go ahead and do is say, okay, here's a blue dot and a red dot. Let's go ahead and say that this right here is 5, this is 2, this is 5, this is 2. So this is 2, 5, and this is 5, 2. And I'm just going to ask a question. Let me do a color here. Let's say I put a dot right, let's put a dot right there. What color should that dot be? Let me do this one first. What about this dot? What color should we color that green dot that I put up there in the upper left-hand corner? Should I color blue or red? Blue. Why? Because it's near something that's blue. I didn't supervise you, I just let you think about it for a second. And that's essentially what neural networks are doing, is they are deciding some sort of boundary, and they're going to computationally decide whether something should be colored blue or red. Now, if we have more data, it's going to constantly update that. And if it has a lot of data, it might be wrong sometimes, like there might be some obscure data points, but really, it's just a linear equation underneath the hood, that if you plug in A and B and C, those are parameters by the model, you plug in X and Y, and if it's greater than 0, guess what? It'll be colored blue, and if it's less or equal to, it'll be greater than red. So that's the idea of neural networks, except for when you're looking at GPTs, you have more inputs, and so instead of 2, you could have 3, you could have hidden layers, and I believe the DeepSeek model version 3 has 600 or 625 billion parameters, not 3. So it's the scale they're doing this, and the crazy part is, these inside nodes with parameters inputs are just really figured out with just trial and error, and that is really what these GPTs are using. So let's go ahead and maybe I'll leave you with a little bit of curiosity to dig into large language models more, but we are living in the future. Why do I say that? Because there was this poem by Shel Silverstein that came out in 1981. It was called The Homework Machine. And it says, "The homework machine, oh the homework machine, most perfect contraption that ever's been seen. Just put in your homework, then drop in a dime, snap on a switch, and in 10 seconds time, your homework comes out, quick and clean as can be. Here it is, 9 plus 4, the answer is 3. 3, oh me, I guess it's not as perfect as I thought it would be. So that is really, we're living in the future in the sense that we have this homework machine, but we are using it for more exciting things for the science majors out here. This came out last August. AI scan developer detected his wife's lung cancer because they fed it a bunch of inputs, and that neural network essentially found the underlying patterns that allowed it to go ahead and detect lung cancer. Dr. Salvatore right here. There's a company called In Silico Medicine who uses AI to essentially progress drugs through and chemicals through the drug testing stage, and you can see some of their drugs placed right now. So it's an interesting world. So I would say there are 2 skills that are more important as we get into these things. So students, I encourage you, be adaptable, be lifelong learners. So as these tools evolve and do amazing things, you're able to use them to really excel in your field and do the work that you are called to do. Thank you. Have a wonderful day.
There's time for at least 2 quick questions here.
2 quick questions.
From me, I have 2, and then maybe some other people.
All right, someone other than Professor Alma?
Wait, so 1, and I'll give you them both at once. 1, what does GPT stand for? And then 2, as someone who struggled so mightily to beat that game the other night in tic-tac-toe, do you really feel that's confident talking about it like as much as you do?
The second one felt like a rhetorical question, so I'm going to answer the first one.
Yeah, it says
So
in there, right?
GPT was really never meant to be a the way we use it, as in like a brand, like ChatGPT. GPT stands for Generative Pre-trained Transformers. So generative because it's trying to generate text or text, video, or pre-trained because it was trained on data, really the internet. And transformer was kind of the extension of the neural networks that came out in a paper in 2017 by Google called Attention is All You Need. So basically, ChatGPT OpenAI used this transformer model to bring about the ChatGPT model. And what attention looks like visually is if you are looking at, does anyone know the capital of Boston? Oh, gave away. Capital of Massachusetts, Boston. Attention essentially looks like this. Initially, before this attention or transformer model, AIs had trouble recognizing the answer to this state or finishing the statement because Massachusetts and state were far away. So most of these earlier models before attention in 2017 did not realize that the answer to this question is, or to finish this prompt out, would be Boston. But once we had attention, we basically, what these transformers do is they tokenize. So they break the statement up into a bunch of tokens, and they do it more sophisticated than just what we have up here. And it computes a value, by the way, to represent Massachusetts in these algorithms. That is how Massachusetts is represented. It is 1,536 floating point values or decimal values to represent the word Massachusetts. So those numbers are fed into that model. Again, the models nowadays have about 650 billion parameters. And it essentially makes these connections. And the attention is saying that Massachusetts and state need to basically have a strong connection to each other. So it sees that, and that is all fed into this large neural network. And at the end of it, it knows that the next word is Boston. So so that is what is neural networks taken to scale extremely where we get GPTs. Yeah.
So in the models that have been created, who decides then what answers they will not answer?
So there's probably, a lot of things are happening where this is huge, so to speed them up, they have kind of, it's called a mixture of experts. So instead of having just one big neural network, it'll kind of have one expert that deciphers the problem and assigns it an expert, which is then smaller trained, maybe it's not as much data. So there's probably an expert that decides that they maybe have a little more control over, because we really don't have much control over these hidden layers, except for here's the data and what do you think, and there's some testing and training set. But there's probably using a mixture expert. I don't know the exact architecture, but.
I mean, if you go to DeepSeek and say, is the communist government of China evil, what's the next thing it's gonna say?
And it doesn't
Let's talk
respond
about
to that.
something else.
Yeah,
So
so
it's like
I have
using
not
the
personally
same
looked
thing.
into it, but I imagine it's using some sort of, some part of the model the humans have a little bit more control of, like when you see this word assigned at a lower probability, because all these are you really doing is probabilities. So it might take specific tokens and say, when you see this token, give it a probability of 0, so it's not used as part of the prediction or the next layer. Great question, yeah. Because
That's so interesting. So I just read an article yesterday about a research thing that was done on a rare disease, and AI picked up a treatment in the databases because it has a large cytokine, a release of an inflammatory chemical, and because it reads that, it read through all things that had that, and all treatments that had been tried in the chart, and then went and found something, and they were able to treat the disease. So it's just that's
quite
just
interesting.
databases linking it. That's so cool.
And I think that's to make the role of the doctor be more about communication and patient care and
Oh, if only.
empathizing, and in a sense building confidence in their diagnosis. So like what happened was like those hidden layers, so it was fed in all those images, and certain nodes are lit up, and this kind of brings up the probability. As it goes through, you can see certain things are lit up, and when everything's said and done, it's going to have it'll return the highest probability result. So you can see 7, it goes in. These hidden layers, 7 is going to have the highest probability, so it says this is a 7. So this is probably the most basic example of deep learning is in image recognition. It's just pixels and how dark or how white in this case the pictures are, or the pixels are the inputs that are fed in. So, but it doesn't have to be pixels, it could be features of a patient.
Yeah, very cool.
Any other questions? Awesome. Well, thank you everyone. Have a wonderful 4-day week.
Cody, are you gonna get an Optimus when I come out? Are you gonna get one of Elon's robots?
Oh,
I want one. I want one now. I wish I could get it now.
Driving your car out to